Okay, in this video we're going to look at a few examples of problems where we're finding a limit as x grows without bound, either in the positive direction or negative direction. So in the last video we looked at where x was approaching a number and then the outputs maybe grew without bound. Here we're looking at limits involving infinity where x is approaching infinity or maybe negative infinity, and we're looking at what the outputs of the function are doing. So for this first example, this is a basic function that you might actually have a good idea what this function graph looks like. So if I were thinking about this problem, I would think about the graph of this function. So I'm going to sketch that. You can also think about it numerically or in terms of function inputs and outputs as well. The y equals e to the x graph is an exponential growth curve. The negative inside here flips that graph across the x-axis, across the y-axis, a horizontal flip. And so you end up with a graph that looks like this, exponential decay curve, and this horizontal asymptote right there. All right, so when I think about that, I want to think about what the outputs of the function are doing, the y values of the function, when the inputs grow without bound, so on the far right end of the graph. And so if you look at that graph and you think about the horizontal asymptote that's there, you can see that those y values are getting closer and closer to 0. They're never actually equal to 0, but the y value is getting closer and closer to 0 as x grows without bound. So we would say here 0. And a justification for that limit could be a graph. You could talk about it numerically. You could think about that as well. So if I were going to think about this numerically, I might think about when x is very, very large, 100, a million, a billion, what happens to the values of this fraction. And so I could think about that. I'm going to put just e to a negative number that is large in size. And so when I think about a negative exponent, that means 1 over, and then e to a positive exponent. So I could think about it like that. This is, again, kind of scratch work, but thinking about it numerically. And so the denominator here would be growing without bound, approaching infinity. The numerator would stay 1, so 1 over, and the denominator approaches infinity. So when you think about the output values of that function, larger and larger and larger values on the denominator, the value of that overall fraction, 1 over a million, 1 over a billion, 1 over a trillion. So the outputs of that function would be approaching 0. So thinking about it numerically, thinking about it graphically, either of those would be support for this answer. Those are all really kind of scratch work, though. This is a basic enough problem. Most of the time, unless you're asked to justify your answer, you could probably just write down that that limit is just 0, thinking about that function. All right, so we're going to think about the same function, but limit as x approaches negative infinity of this function. So I'm going to think about the graph since we have it over there. So we want to think this time about when x grows in size without bound, but in the negative direction. So on the graph, that would be on the far left side of the graph. And we want to think about what the function outputs are doing. So that would be here. So we can think about as x grows in size without bound, or goes far left on the graph, what happens to the y values? So they're headed up. So for this one, we would say that that limit is positive infinity. Again, you can kind of think about it numerically. If x is negative and large in size, but I put it in here where we already have a negative, I'll end up with e to a very large positive number. And that will grow in size without bound. So that will approach infinity. Just thinking about it numerically. All right, so two different limits there involving infinity. Notice our answers. One of them involves infinity, and the other one's just a number. Just as another point of contrast, let's look at one other kind of basic function. Let's look at the cosine function here. All right, so this is asking us about, as x approaches infinity, what happens to the outputs of the cosine function. This is another one that you should have a good sense of what the graph of that function looks like. So you might sketch that. I'll just do that in a different color over here. All right, so cosine wave, thinking about that, and thinking about as you go to the far right end of that graph. So when you think about this, that's going to just keep bouncing up and down as you go all the way as far as you can keep going to the right. So the output values of that function are not approaching a number like they were for the e to the negative x1, where the output values were approaching a number 2. The output values of the function are not growing without bound. like the output values were here. They're just continuing to bounce around back and forth. So the output values are not approaching a number. They're not approaching infinity. The output values are not approaching negative infinity. And so there's only 4 possible answers for a limit problem: a number, infinity, negative infinity, and then if none of those is what happens to the output values of the function, we say that the limit does not exist. So this is one where the limit does not exist. Occasionally I'll see students try to write something like plus and minus 1. So the function bounces back and forth between output values of plus and minus 1, but the function outputs do not stabilize at 1 or negative 1. They continue to go back and forth in between and hit negative 1 and positive 1 and every number in between infinitely many times as you continue on out to the right. So does not exist on that. So number, positive or negative infinity, or does not exist. Those are your 4 possible answers for any limit problem. All right, let's look at one other one here, kind of just a basic function that maybe you have some sense about what the graph might look like. Okay, so I've written down here a 3rd degree polynomial, and we are interested in the limit as x approaches infinity of that. And while you might not know exactly what this graph looks like completely in terms of x-intercepts and y-intercepts and things like that, from algebra you should have some sense about what is called end behavior of this function. And so that's really what we're after here when we're thinking about limits as x approaches infinity and negative infinity, is the end behavior of the function. What's happening when x grows without bound? So for this one, we're interested in the far right end of the graph as x approaches positive infinity. And from algebra, you probably have some recall, hopefully somewhere in your brain, about an odd degree polynomial. The degree of the polynomial controls the end behavior of the graph. So odd degree polynomial with a lead coefficient of 1 is going to have end behavior like an odd power function. So similar to the graph of just y equals x cubed. So on the right end, you're going to be up. On the left end, you're going to be down. And so as x approaches positive infinity, this will be controlled by this x cubed term, and those outputs will approach infinity. Numerically, thinking about this, we've kind of already talked about that as well for the other functions. So numerically thinking about this, when x is very large, the term that really dominates this function and controls the overall outputs of the function is the x cubed function. So sometimes you'll hear people talk about limits like this in terms of the dominant terms and thinking about the dominant terms. So you might think about just this part. When x is large, these parts have negligible effect. One caution about thinking about dominant terms is that really only works when you're thinking about end behavior of a graph. So limits as x approaches infinity or negative infinity doesn't work when you're thinking about, say, the limit as x approaches 2 of this function. I wouldn't be able to just focus on the one dominant term. All right, so same function, one more limit. And let's look at the other end behavior as x approaches negative infinity of this same function. So that would be asking us about the left end behavior of the same function. So again, we can think about the function graph as x approaches negative infinity. Y is going to approach negative infinity as well. The y values are going down. So negative infinity for that. You can also, again, think about this numerically. When I think about dominant terms here, since x is growing large, I can just focus on the dominant term. When x is negative but large in size, and I cube it, I'm going to get negative numbers that keep getting larger and larger in size. So negative infinity for that one. All right, we'll look in the next video at some slightly more complicated examples of limits involving infinity where you may not be able to just look at the graph, but you'll need some other techniques to evaluate those.